Here's another reaction. This is iron 3 oxide reacting with carbon as graphite. It makes iron metal and CO2. And what we can do to figure out the values here, you can first find delta H, products minus reactants, and that comes out to be positive 467.9. You can then find delta S, products minus reactants, comes out to be positive 560.3 joules per Kelvin. And at room temperature 298, delta G, positive 300.8 kilojoules. Now, positive delta G's mean this reaction is reactant favored at room temperature. And that means this reaction will not occur, all right? It's not going to happen at room temperature. However, let's say you have a lot of iron 3 oxide and carbon sitting around, and you'd love to make it happen. You'd love to turn it into iron and carbon dioxide. Well, if you look at the delta H and delta S values, delta H is positive. So this is not an enthalpy-driven reaction. Negative delta H's are enthalpy-driven. Enthalpy really doesn't want this reaction to go. On the other hand, delta S is a positive number. This reaction is entropy-driven. Entropy wants this reaction to go. So here you've got a condition where both delta H and delta S have the same sign. If they're both positive or both negative, temperature is going to play a factor. So what I'd like to do in this next part, let's figure out the threshold temperature by which delta G will go from being positive, which it is at room temperature, to negative. And so what we're going to do, we're going to see some temperature. It's going to be a value higher than 298, and we're going to calculate it. And that's where you go from having a positive delta G to a negative delta G. And so whatever temperature we calculate, that plus a few extra degrees will turn delta G into a negative value. And it's not too hard of a calculation to do, but this can be really important. So because we know this is entropy favored, we want to figure out the temperature at which we'll change the delta G from a positive to a negative, turn it from a non-spontaneous to a spontaneous reaction. And what you can do is just let delta G equal 0. And so 0 equals delta H minus T delta S. So delta H equals T delta S, if you put it on the other side. Solve for temperature. Temperature is delta H divided by delta S. Now again, turn delta S in joules per Kelvin into kilojoules per Kelvin. But you can see what happens there. You end up with just a Kelvin temperature. And in this problem, that's 835.1 Kelvin. So temperatures larger than this will give you negative delta G's. So if you can have your temperature be ran at, like, say, 850 Kelvin, all right, just a little bit more than 835, that's going to make your delta G a negative number. And negative delta G's are the ones that are going to happen. So again, if you've got a lot of iron 3 oxide and carbon and you really want them to react, it might be worth your time to have it run at, say, 850 Kelvin or something larger than 835.1 anyway, because at that point, the reaction becomes spontaneous. It will start occurring, and that might be worth it. And if you run a business, all right, maybe it's worth it then to have some kind of relatively expensive thing to get a temperature higher than 835.1 Kelvin. That's really, really hot. However, above those temperatures, that's where this reaction will occur, and that might be worth your time and investiture of resources to get it. That would turn your iron 3 oxide and carbon into iron and CO2. So figuring out the threshold temperature can be really important. It's only for conditions where delta H and delta S have the same sign. If delta H and delta S are both positive, the temperature you calculate, temperatures larger than that, will be spontaneous. Now, if delta H and delta S are both negative numbers, you can also calculate a threshold temperature, and then temperatures under that will be spontaneous. Honestly, it's more likely that you're going to have both positive, like here, but if you do see it, that's what that would mean. So again, delta H and delta S, if they have the same sign, then calculating threshold temperatures is important. If you end up with delta H negative and delta S positive, or vice versa, your temperature comes out to be a negative Kelvin. And again, that doesn't fly in science, so that'll tell you then that this doesn't make any sense. But if they're both the same sign, these threshold temperatures can be really important. Here's an example of ice going to liquid water, and we're going to figure it out at 273 Kelvin. All right. Well, delta H, if you figure out this transformation, is a positive number, but delta S is a positive number. So delta H equals T delta S, and it's negative above a certain temperature, and it's also then positive below a certain temperature. So if you want your ice to melt, the water has to be, of course, above freezing, which would be above 0 Celsius, above 273 Kelvin. So say at 298 Kelvin, then the entropy term is able to overpower the delta H term, and you end up with a spontaneous, i.e. negative delta G. On the other hand, at temperatures less than 273, then the opposite's going to happen, and your ice will stay the same. So this is kind of a practical use of all this stuff to figure out how ice melts. And of course, if you want your ice to melt, it has to be at a warmer temperature. On the other hand, if you want your ice to stick around, you should have it at a temperature less than 273 Kelvin. Here's a question. A given reaction is not product favored at room temperature. So what that means is delta G is going to be a positive number at room temperature. And then it says at what temperature will the reaction become product favored? And there's delta H and delta S. Well, the important part here, once again, is temperature is going to equal delta H divided by delta S, but you have to make sure that you turn delta S into kilojoules per mole to make this happen. And the temperatures come out to be Kelvin. You can translate to Celsius if you want to, stuff like that. So for this problem, it would be delta H, the 50 number, divided by delta S in kilojoules, which is 0.1, all right? 50 divided by 0.1 comes out to be 500, so the temperature here would be 500 Kelvin. And then temperatures just slightly above that, you would have negative delta Gs. So if you want this reaction to go, you could have a temperature just a little bit above 500 Kelvin, and it would start to be spontaneous.